I'm Alex from LLEAF. It stands for Luminescent Light Emitting Agriculture Film. So me myself, I'm an industrial chemist with my partner, and we started LLEAF when we were in UNSW, and we work with luminescent materials. So we're looking at how we can use luminescent material in agriculture, and we've been supported by ARC Linkage Grant, CRC Future Food System, the CRC. And we are part of the Cicada Innovation portfolio company that's based in FLE. I'll tell you a bit of the technology. So basically, it's based on fluorescent or luminescent dye that's absorbed and emit light at a different wavelength. So what our material does, as you can see here, especially the orange one is especially bright because that's what our eyes is most sensitive to. It takes some of the green light from sun spectrum and then shift it into the red region. So we have formulated a specific fluorescence dyes for horticulture application. And when it's embedded into the material, in this case, plastic, it will be randomly aligned and omnidirectional, meaning that it will also diffuse the light. So it's also give you that diffusive effect, which is beneficial for the plant to grow. We have 2 patents that have internationally filed, with one of them has been granted, and we manufacture them at the moment into polycarbonate plastic, but we also work with other potential carriers. So just to show a little bit what our material actually does. So for example, at the top here, it's what a typical sunlight solar spectrum. And we've seen a lot of vertical farmings, indoor farming that's using LED to grow their plants. So they already do a lot of research and product development from their side and learn that the blue light and the red light is the most beneficial. But it's not like the plant don't need green, the plant also need greens. So we take that knowledge from the LED world. What they're doing is an active technology because they change electricity into light, and we apply it into our film. So we consider it to be a passive light. As you can see, this is the spectrum of what happens if you put our film underneath a sunlight. So you lose a bit of the green and the yellow, and you get more of the red. This is the comparison. So we've tested many different colors, many different combination of colors, and we come up with 4 potential products. With the first one is the color is red, so called LLEAF RED, and that is targeting the chlorophyll for in general increasing the yield. We try orange, but it doesn't work as well, so we discontinue that. And we are also developing the blue and purple color. This two is a bit more interesting because it's actually not focused on the chlorophyll. It's focused more on the phytochromes of plants, which these two, the purpose is more to modulate seasonality and combine the benefits of the season, the time of the flowering and fruiting of the plants. Just to show, to demonstrate how this thing works. So this is a very small, let's say, models of a greenhouse. On the right-hand side is what a typical greenhouse looks like. And on the left, we put our film inside the greenhouse, and I have the film behind me. So this is how it looks like. It looks cooler in real life. Please believe me on that. Because the light, when the plastic play with the light at different angles, that looks cooler. But in terms of how it works, so this is 2 plants that have the same seed. All we did is put water, and as you can see, the one with our film grow faster. And this is outside in the balcony. So the benefits that we expect is increased chlorophyll production, reduce the stress, increase the yield at the end of the day, possible decreased growing time, and something that we will test later is a modulate the seasonality. And this is in the facility in Western Sydney Uni that we work very closely with Professor David Kishu and his team. So we put that into one of the glass house. This is a drone picture from above of the glasshouse facility with our film, the one that is looks colored pink here. So hopefully, if all things works out, then maybe when the previous panelists talk about looking at the geolocation, then maybe when you look at the satellite image, a lot of protected cropping Australia will look red, which will look quite funny and cool. So these are the results. Sachin, especially, and Chelsea, who work in Western Sydney Uni, collect all the data about the temperature, the light intensity, and the power. And in this case, the first trial was done on 3 cultivars of lettuce. And as we can see here, compared to the control, the white color bar graph, we have an increased yield of about 14% to 27%, depending on the cultivars. And what we notice is our film or the shifting of the light is more beneficial when the plant is already growing in an optimum condition. Because what we realize is the red cost lettuce just doesn't grow very well in this system, and the impact is not so big. And at the moment, we are doing cucumbers, so hopefully the result will come out in the early next year. And we also having another collaboration also with Western Sydney Uni in New South Wales Department of Primary Industry with Professor Priti Krishna and Dr. Sophie Pax. And in the blueberry, what's been happening is blueberry have a higher nutritional content when it's grown without cover, but it has higher yield when it's grown under cover. So the background of this project is we want to see, can we optimize the yield with the nutritional content by shifting the lights and modulating the intensity. A bit of how the material looks like. It's a thin film of polycarbonate. It's a strong greenhouse plastic, and it's quite easy to clean and to cut. So we are still doing a lot of product development to make it into other forms of final products, and hopefully that will cater for different type of greenhouses or protected cropping as well. In terms of sustainability, that's a big focus of our company, because the premise is we want to optimize what is resources that we have, and natural sunlight is an obvious natural resource, and we want to optimize that for increasing food production. By increasing the food production per square meter, automatically we will also reduce the inputs like water, nutrition, the other emission per kilogram of food that is produced. This is something that we haven't calculated quantitatively, but we know that it's embedded in the inherent property of the product. And also we expect that the product can last quite long, given that it's a long-lasting plastic, and at the end of the life of the products, it can be feedback to be recycled for other purposes, like building materials. So we are very focused on the production side in the sustainable food system. Yep, that's a brief introduction of LEAF, and thank you very much for all our partners in UNSW, HIA, Western Sydney Uni, and we got funding as well from New South Wales government.